All right. This is 2018, number 3, I think. Pretty sure. Yeah, 2018, number 3. All right. So we got 2 wires. Gives us a little bit about their orientation. Tells us that I1 is equal to I2 is equal to 2I, and in the direction shown, held in place, so they're not able to move. Current in wire 1 is directed out of the page. Distance D above the wire 2. Point P is horizontal distance from wire distance D above wire 2. Express your answers to part A, B in terms of I, D, and physical constants as appropriate. So we only get 2 variables to use there. Use Ampere's law to derive an expression for the magnitude of the magnetic field at point P due to wire 1. They give me a whole lot of space to do this, so I might have to do it like up in this space up here. But first, we need to determine the magnetic field at point P due to Ampere's law. So I'm going to use a little bit of symmetry and draw my Amperian loop terribly unsymmetrically. That was really the goal. Maybe I should try and use this inked shape thing. I think it'll let me draw a circle. And it'll be like, yeah, that was a circle. Ah, it did. All right, that works. I don't want any fill, though. Get the fill out of here. What a great circle I just drew. Freehand. Really, everyone's really impressed. Can I just move it over a little bit? It's not going to let me move it. All right, well, it's close enough to being where it needs to be. So we have our circle, my Amperian loop. We'll pretend that it actually goes through point P like it's supposed to, but it's close enough. So if we want to find the magnetic field at P, right, we'll have to use Ampere's law. So we're going to take the integral of B. I still have ink to shape on. B dot dl equal to mu naught times I enclosed. All right, so that's the equation we're working with. The nice part about the little symmetry that we use here, right, we know that wires create magnetic fields that circle around them and vary with radius. So B is going to be constant because everything on this circle is the same radius. So the B kind of hops out here. And we get the integral of dl, which is just the length of this circle, which we should know because we know how long it is around the edge of the circle. It's 2 pi times d, right? 2 pi r radius equals mu naught times I enclosed. We have only enclosed I1, which is I. And there we have pretty much our equation. We just have to solve for B. So B is equal to mu naught I times 2 pi d. And so that goes right here for part A. B is equal to mu naught I over 2 pi d. Derive an expression for the magnitude of the net magnetic field at point P. That one's a little bit trickier because, actually, do I have space down below here? All right, I have some space down below. So I'm going to do this one below where we derive an expression for the magnitude of the net magnetic field. So this is B. At B, or at point P, we actually have 2 magnetic fields, right? We have the magnetic field that's created, if we do our right-hand rule, up from wire 1, right? So we have a magnetic field created this way from wire 1. But we also have magnetic field from wire 2, right? And wire 2 is passing to the right, which means we actually have magnetic field into the page. So X, right, at point P as well. So we have 2 magnetic fields here that are both vectors. So we kind of have to do some vector addition to figure out what the total magnetic field is. This is the magnetic field from 2, right? They're perpendicular to each other, so we can just do Pythagorean theorem to figure out what the total magnetic field is going to be there. So B1 and B2. Interesting to note that B1 has a current of I, B2 has a current of 2I. So B2 is just 2 times B1, right? It's twice as big. So we're going to use the Pythagorean theorem to find the net magnetic field. It's going to be the square root of B1 plus B2, B1 squared plus B2 squared, right? Oh, wait, I wrote square roots. Idiot. B1 squared plus B2 squared. We know that B2 is twice B1. Can we use that to make this easier? This would just be 4B1. This would be 5B1 squared. Can we do that? So if we simplify this, right, if we know that B2 is equal to 2B1, right? Oh, wait, no. Well, let's just work it out, whatever. We could probably make that easier for ourselves somehow. I wrote B2 is twice B1. So, okay, well, let's substitute that in. Let's see if we can make this easier. B net is going to be equal to the square root of B1 squared plus 4, right? Because we square that 4B1 squared. So that'll give us 5B1 squared. So B net is going to equal root 5 times B1, right? We add those together, that'll give us 5B1 squared. We can separate that out and take the root 5 there, and then we just have to multiply that by B1, which we know from up top already is equal to mu naught I over 2 pi d. And that should give us our answer for net magnetic field. Easy peasy. So there's net magnetic field. That's part B. Derive an expression or calculate the numerical value of the angle to the horizontal. So the angle to the horizontal. That's a little bit trickier. If point P is here. The hard part about this is figuring out what angle is to the horizontal. So if I kind of set this up and turn it sideways so that we can see B1 and B2 at the same time, B1 is going, this is C, B1 is going up and B2 is going to the side. It's twice as big. So this is B2. This is B1. We want to figure the angle to the horizontal. So we want to know, like, when we combine these two vectors, what's the angle to the horizontal? So I'm actually going to move, do a little vector addition. I'm going to move B1 over to the other side of B2. So here, that means our net force that or our net magnetic field we found was right here. This is B net. And the angle to the horizontal, you can see B2 is the one that's on the horizontal. We can see that going up here too, right? B2 is in the horizontal plane, B1 is in the vertical plane. So we really want to know what's the angle to B2 between our net force or our net magnetic field and B2. So that's what we have here. We could really use any equation we wanted now to figure out B2. I used inverse tangent. So tan -1 of tangent is opposite over adjacent, so I don't know why that's B2, that's B1. B1 over B2. We know that B2 is twice B1, so we get tangent of B1 over 2B1. B1's cancel, leave us with 1/2, so we get the inverse tangent of 1/2, which is equal to 26.6. degrees. So this angle here is 26.6 degrees. And that gives us part C. So the only tricky part there was being sure that we were finding the right angle and not finding the angle to the vertical by accident. Wire 1 is now released. Which of the following best describes the initial motion of wire 1 due to the magnetic field of wire 2? Assume no gravitational effects. So we don't have to worry about gravity. So I think the easiest way to look at this one is from this perspective. All right, so we know wire 2 creates a magnetic field, right? And the magnetic field, because of wire 2, goes into the page on the left side, or on the top, right? Into the page on top and out of the page on the bottom. And then directly over top, it's going up the page. It's going up the page on top. So if we look at a couple different points on our wire 1 here, right? Right above here, right? If we look at this point on wire 1, the current and the magnetic field are in opposite directions, right? Current is going this way. Magnetic field is going upward. They're in opposite directions, but they're parallel, which means there's no force, right? Because F is Q, B, B, sine theta, right? So if theta is 0, sine is 0, and we get 0 force. So there's no force here at the middle. But if we look at some points over here, right? If we look farther, oops, I drew that current the wrong way. If we look at current farther up here, right? Current's still going here, but now the magnetic field is pointing downward, right? And now they're perpendicular, so we could actually get a force there. Current is going down, right-hand rule, magnetic field is going into, which means I'm getting a force to the right. So I found a force to the right on top. If we look down at the bottom, we have the exact opposite, right? Current going down, but magnetic field coming out of the page. So we can look at a point down here, right? Current is still going this way. Magnetic field is coming out. So I get a force. You guys can't see it. I'm twisting my arm, but the force is to the left. So down here, we get force to the left, which means if we look at the net force, right, we had no force in the middle. We had force to the right on one side, force to the left on the other side. There's going to be no net force, right? Those forces are going to cancel, but those forces will cause rotation, right? Because they're in opposite directions at opposite ends of our wire. So the wire 1 will rotate, which way did we say? Clockwise, as viewed in figure 2. All right, because of the way that the right-hand rule works. And we kind of just justified it there, but if we have to state our justification, towards the top, how do I want to say this? The top of wire 1 feels a force right. The bottom feels a force left. This causes rotation. Clockwise rotation. Cool. So there is the first section there. If we slide down to the second section, wire 1 is replaced with a conducting rectangular loop of length L with W resistance R. The loop is placed a distance D from wire 2 as shown. The loop wire and distance D are all in the plane of the page. The long side of the loop is parallel to the wire. The current I2 for wire 2 is decreasing linearly as a function of time according to equation I2 equals 2 I naught 1 minus KT, where k is a positive constant with units of s to the minus 1. Of the following, select the integration that will give an expression for the flux as a function of time. So we need to figure out flux, all right, as a function of time. So our equation for flux, and this flux is equal to the integral of B dot dA. Okay, so we have to take that integral B dot dA and eventually match it with one of these equations down here. So how would we do this, right? What would we do? Well, my initial thoughts, right? It's B that's changing. It's not A that's changing, but that's something to consider later, right? We did something that was similar to this in class, right? When we had a variable magnetic field, because the magnetic field at the bottom is much less than the magnetic field at the top here. So we split this up into strips of loop, right? So we have little areas there, little areas dA, right? Where dA is equal to this little distance, which I'm going to call dr because we're talking about radiuses away. The magnetic field equation is based on d, which is essentially a radius away from our wire. So I'm going to call these little drs that has a width L. So we can actually say that dA is equal to dr length or width times L. And you should probably switch those, but whatever. So we have a way to replace dA. Let's talk about B, right? B is equal to mu naught I over 2 pi D. Again, we said D is a constant value. Right now we don't have constant. So I'm actually going to replace this with R, right? Which is the variable radius that we are away from our wire. So mu naught I over 2 pi R. And the last kind of substitution we need to make is this I is not fixed, it's variable. It varies as 2 I naught times 1 minus KT. So we're actually going to have B equals mu naught times 2 I naught times 1 minus KT over 2 pi R. And then we can take all that, right? We can take our dA, we can take our B, and we can substitute that in for our flux equation. So flux is going to be the integral of mu naught 2 I naught 1 minus KT over 2 pi R times LDR, right? Length times width, which is what we were substituting in for area. So this section was magnetic field. This section is area. And then I think we have the correct expression pretty much. We just have to determine our bounds. So if we look at this, mu naught 2 I 1 minus KT LW, we didn't have a W in there. Mu naught 2 I, we didn't have LW. Mu naught 2 I LDR. So it's either one of the bottom ones. We just have to determine what the integration is going to be. So our little sections of area are going to go from D up to here, but this value, right, goes from D up to here. This is D, this is D plus W. So our bounds are going to be from R equals D to R equals D plus W, which is number 3 there, the third one. Right, this one has the wrong bounds. W, it looks like, is smaller than D. So if you did from D to W, you would be doing from this distance down to that distance, which doesn't make any sense. I didn't see this until after I went through this the first time, but you could have also just looked at this right here and figured out which one of those integrals would give you this answer, right? This is the answer for the integral. So if you looked at this and you're like, okay, it's the third one. The third one gives me that integral. So I didn't see that until after I did it. But if you're better at math than you are at the physics part, there's an easy way to get the answer. Derive an expression for the magnitude of the current, if any, induced in the loop. Express your answers in terms of I naught, D, R, W, K, L, and physical constants as appropriate. So first, let's figure out, are we going to induce current in the loop? So we said I was decreasing linearly. So I2 is producing magnetic field that goes into our loop, right? The magnetic field is this way. And because I is decreasing, this magnetic field is getting smaller. We're getting less magnetic field. I'll draw some smaller X's, right, to show that our magnetic field is getting weaker. Induced magnetic field will act to oppose that. If we're getting weaker magnetic field going into the board or into the page, our field or our induced magnetic field will try and bolster that up, right? Doesn't like that the current's or the magnetic field's decreasing. So it is going to create magnetic field into the page to support that decreasing magnetic field. So magnetic field into the page would cause current going around clockwise. So I think that yes, we definitely have current. It is flowing around clockwise, which is actually the next answer here. We get clockwise current, but let's determine or derive an expression for the magnitude of the current. So we're going to start with Faraday's law, right? EMF is the absolute value of d phi dt, right? Flux over time, change in flux over change in time. We have an equation for flux, right? We have this whole big thing right here. So we could actually just pop that in for flux. So we're going to get E equals d dt of mu naught I naught L times 1 minus KT over pi times the natural log of d plus W over d. Right, we get the time derivative of this whole thing right here. Now, this is a little bit nice because a lot of this is constant, right? This is a constant, this is a constant, constant, and doesn't have anything to do with t. So we can think about it basically as a coefficient in front of this thing and pull that all out. So we'll get the EMF is equal to, I guess everything's positive, so we don't really need the absolute value, but actually we do get a negative t here, or a negative k here that will cancel out. But we can pull the mu naught I naught L over pi times natural log of d plus W over d out and in front, and then just worry about the time derivative of 1 minus k times t. And the time derivative of 1 minus k times t is, this goes away, right? Derivative of 1 is 0. Derivative of negative k to the t is negative k. So that pops out. Negative sign disappears because of our absolute value. And we end up with mu naught I naught L k over pi times the natural log of d plus W over d equals the EMF. And then the last step, right, because it asks us for current, we can replace EMF with I times R, right? I times R goes in for EMF. We divide R to the other side, and we can get the I, which is what it asks us for, right? Current. Derive an expression for current. Yep, I is going to be equal to mu naught I naught L k over pi R times the natural log of d plus W over D. Voila. There is our expression for current. And we answered this last part already, right? It's going to be clockwise, and we kind of determined that because our magnetic field into the loop was decreasing, which means we are going to create more magnetic field into the loop to bolster that. That's magnetic field into the page. Induced current must be clockwise. So there is our answer for 2018 number 3. Good work, team.